two lessons in one because Monday you're going away. Sorry about that. But I actually stay out here about midnight to finish the second lesson. All right, let's start. So, talking about log scale, you need to understand what a log scale is. So we'll talk a little bit about the advantage and disadvantages of a regular Cartesian plane with linear axis and when graphing logarithmic relationship. And then we need to be able to graph some logarithmic relationship on semi-log and log-log axis. We'll think about what happened when we plot those graphs on semi-log or log axis and solve problems using semi-log and log-log axis. All right? So I'm going to start off, ask you to look at the two things, linear scale and log scale. What is the difference between linear and log? Sorry? It's positive, yes. And what else? Think about when you go from one to the other, it's adding, and this one is
adding a power.
Multiplying, correct? So one is add 10, the other one is multiply by 10. So you can see that the difference is this is linear, this is non-linear. So you're going to keep on multiplying by 10. Now, so let's have a look at the log scale itself. What I have done here, I have just enlarged this bit, 1 to 10. So that is 10 to 100, 100 to 1000. All right? That's 0.1 to 1. So I'm actually going to use this to illustrate what happened to every single bit. All right, from 1 to 10, 10 to 100, 10 to 1000. All right? So here, you can see that this is a log scale. Where do I actually do all this tick mark here? Where is 2? Where is 3? Where is 4? Where is 5? Where is 6? Where is 7? Where is 8? Where is 9? How do I actually get that? You don't know. That's fine. So here, if you think about that, log 1 is 0.
Yeah.
Log 10 is 1. Correct?
Yeah.
Now, so if that is 1 unit, what is the proportion of this in terms of 1 unit?
110.
It's not 110? Sorry? Okay. Let's what about take the log of 2? So, 10 to the power of x is 2. So x is log of 2. So this point here, if it is log of 2, it would be 0.3010. So distance from here, it occupies 0.3010. Got it? Yeah? Happy with that? So now, here, let's think about that point over there. Notice that every power of 2 is equidistant from each other. So if you think about 1 to 2, 2 to 4, 4 to 8, those distances are equidistant. So I'm going to highlight that. Oops. Going to highlight that. This distance is actually equidistant to that, 2 to 4 and 4 to 8. Why? Why is that so?
Because it's scalar multiple.
It's scale of 2, but think about that. That is, all right, let me write it on the screen. Make it a little bit easier.
It's like 2
That
times
is
log of.
log of 2, correct?
That's log of.
This
2
is log
squared,
of 2 squared, which is 2
log.
log 2, correct? So, therefore, this distance is the same as this distance. To 8, sorry, I should highlight it to 8. So this is 3 log 2, correct? Yeah? So you should see that that is equidistance. That's that point over there. All right? So with that, can you actually tell me where 5 would be? Where would 5 be? All right, where would 5 be?
Log 5.
Place log 5. So if you work out, that will be about 0.69. So it's not right in the middle, it's 0.69. Think about this whole thing as 1, so that's the proportion. All right? So now the distance from 1 to 2 is actually the same as distance from 5 to 10. All right? Let's work out log 3 on the logarithmic scale. Where is it placed? And then let's try to answer that question. Oh, actually, no. Hang on. The reason why I say that is it's the same is because 1 take away that bit is the same as there, which is where that point is. All right? That point.
0.47.
Okay, so that would be
0.47.
0.47. All right? So if that's 0.47, can you work out 6 and 9?
You can work out 9.
You can work out 9 based on 3, correct?
Yeah.
Yeah? And then you can actually work out, once you work out 9, all right, you can work out 6, which is,
9 take 3. Oh my.
6 is distance from 3 to 6 is the distance from 1 to 2. That's all. All right? Same as this, the idea here. Distance 3 to 6 is the distance from 1 to 2. Same as the idea of 5 to 10. All right? So finally, 7, you've got to calculate and work out where the location is. That's it. All right? Now, dot, dot, dot just means that it goes on and on and on and on. That's all.
No clue.
All right?
Wait, so
Here,
why is the difference from 3 to 6 instead of 1 to 2?
sorry?
Why is the difference from 3 distance from 3 to 6 instead of 1 to 3?
Because look at the 3 and 6 based on this thing. How you calculate that? 1 to 2 is 1 over 6. 3 to 6 is, all right? 3 to 6 is that. Take away that. All right? That 1 to 2. That is double that. If you look at the log, this is log 3, right? This is log 6, which is log 2 times 3. Yeah?
Log 2.
2 times 3. Log 2
Log 2 plus
log
log 3. Right.
plus log 3. Yeah? Yeah.
So how does that explain the first one?
Where's log 2? Sorry?
The 1 and 2 and the 5.
1 and 2 is a 5. 5 is 0.69. So 1 take away that. 10 take away that. That's 1 take away that. It's equidistance for that. That's all. 0.31. Okay? I mean, all this, you really don't need to know that. As long as you know the log, you can plot the point. But let's not worry too much about that. So, the most important thing for you to know, this is just trying to show you what log scale is like. Alright? It's not linear. So a log scale is a scale of measurement for which the relatively large or small quantities are represented in using a more manageable numbers. So things like Richter scale, pH scale, and decibel, loudness, all those are logarithmic scale. I will go through that and do some examples a little bit later. Now, why do we need log scale? Log scales are useful when the data you're displaying is much less or much more than the rest of the data when percentage differences between values are important. So if you look at something like this, these are the same graph. Revenue by production line and revenue by production line. This is plot on a linear graph. If you look at the linear graph, that is actually really small. But if you plot on the log graph, you can see that that actually is not that tiny. All right? So sometimes it's useful when you plot graph. Especially for me, when I was an engineer, I would use log or semi-log graph to do a linear regression. It's a lot easier that way. And then I will transform it back. It's just a transformation.
What is log?
All right? So here, if you look at two things. Here, when we plot this graph here, it's an exponential graph. What is this? Y equals to what? Can you work it out? Y equals to
Log 2.
log or exponential?
Exponential.
Exponential. So it is exponential, and it will be, look at this point. Yeah, to the 12x. So what I've done is, if I plot it in the normal Cartesian plane, linear and linear, here you can really it's really hard for you to tell the difference between those points, correct? Yeah? But if I take a log here, which means I have actually enlarged this bit. Yeah? Enlarge this bit, 10, and then enlarge to 10 to 100, and enlarge 100 to 1000. So when you plot it in that situation, you actually get a straight line.
So you just plotted log base 10 of that exponential.
Basically, what you would do is you'll be given a graph like this.
Yeah.
It's the same. This will be 8. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. 11, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 100, 200, and so on and so forth.
So it's not an even spacing.
Yeah, it's not an even spacing. So what happened is you have enlarging the bottom bit, and you can actually see that as a straight line. So for me, like I say, some of the work that I've done as in my engineering work is I need to be able to use the whole range. So I actually can't really fit a line here. I have got to take it to a log.
That's
Semi-log.
log base 10, right?
Yeah, log base 10. Yeah,
So you're just
semi-log
taking
logs.
the
Log base 10.
of that exponential.
Yeah.
essentially.
You do log base 10 is because you do really need to plot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
So you always use log base 10 in this
Yeah.
situation. All right. So now the semi-log graph. There are two types of semi-log graph. You've got a log linear, where the log is on the y-axis, or linear log, where the log is the x-axis. Now, can you notice the difference in the first one? Which one is a straight line?
Red.
The red is exponential. This is just fx equals to x, like y equals to x, which is a straight line in the linear, but in this situation, it's a curve. And when it is a log, it is a curve. So if you do a log linear graph, when you plot an exponential function, it is a straight line.
Yeah.
Whereas a linear log graph, exponential is a curve, fx equals to x, which is a straight line in linear, becomes a curve, and log x becomes a straight line. Yeah? Because you are taking the log of x here, the x will be straight line. Whereas this one, you are taking that to exponent of 10, so therefore, if this is a log scale, this is a straight line. All right? Now, example 1. Can you show algebraically that all exponential relationship of the form of y equals to AR to the bx will appear as linear relationship of log linear scale? The way to do this is actually take log base r of y, the left hand side, the right hand side, log of base r. So if you take log of base r, you know that log r y equals to log r brackets ar to the power of bx. Now, using your log laws, you should be able to split that out, which means log r of y equals log r of a plus log r of r to the power of bx. Now, what would this be? Log r of a. A is a number.
Point as well.
It's just a constant. Yeah, it's constant. Now, what are you going to do in this case? What would that happen? Log r of r to the power of bx.
Pull out the BX.
It will become
Yeah.
bx. So therefore, in this form, compare that to y equals to mx plus c.
Yeah.
Log y is y, log r of a is c, n is the b, and x.
Wait, sir.
Yep.
But don't you always use base 10 for the log? So,
No, you don't have to.
or you don't have to.
You don't have to. You don't have to. But
For
I
this
want to use this as a generalization to show how you get that.
If you took base 10, would you still get a straight line?
Which base 10, yes, you would definitely get a straight line
Just
as
a
well.
different form.
Yeah, just different form.
Okay, yeah.
All right. So now, can you describe the gradient of the line formed by this?
Use log
All right.
both sides.
So if I use log of base 10, what would happen here? Log of base 10, now I'm doing base 10 now, log of y is variable because y changes based on x, right? So now if y to the equals to 2x, if I plot a log linear graph, I've got log 10 of y equals log 10 of 2x. So therefore log 10 of y equals x times log of 2. And what is log of 2?
Constant.
It's a constant. It's a gradient. Correct? So in this context, what it is saying that for every increase of x, there's an increase of log of 2. That's all. All right?
Yeah.
Pretty. It's just a matter of interpreting it. All in context. So that is the log linear. I generally, in my situation, I've used a lot of log linear. I haven't really used a lot of linear log. Because I do, when I was modeling, I did a fair bit of exponential. So I need to bring it to a straight line, so I use a log linear. I seldom use log to actually model something. All right, now, so can you actually therefore graph this on the log linear scale? First, you need to change it to y equals to mx plus c format.
Increase x once.
All right?
2x
So
plus
how do you change that?
log 7.
So here, I give you the y-axis is a log 3, log of 3.
What's log 3?
All right.
That is...
So log of 3, basically this is 3, this is whatever.
It's 3.
If you work it as a linear.
2x plus
So this
3.
is log of 3. So what you could do in this situation is take log of 3 on both sides. Take log of 3 on both sides.
This today.
Why are you doing base 10?
All right. Here, once you have done that, you should be able to work out
Definitely pretty good.
that is actually log of 327 plus log 3 of 2x, correct? 3 to the power of 2x, yeah?
Yeah, which is
Got it?
2x plus 3.
So let's just become log y is 3 plus 2x or 2x plus 3.
Yeah.
And then of course, here you can start off with the y-intercept is 3.
Yep.
And keep going to x to x to x until you get all the point. All right? Oops. Until you get the points and you can draw a straight line. So remember, this is no longer linear.
No, that's
This is just a log. The scale here is a log scale.
2x.
And that is a linear scale.
3.
Log linear.
There you go.
Can you hold it down? Actually, doesn't go the other
All
way.
right, moving on. Now, it's just a generalization of semi-log function. So on the log linear plot, you've got log y equals to mx plus c. Whereas on a linear log plot, it has y equals to m of log x plus c, where r is the base of the log scale. That's all. All right? So it's a different way of thinking about where your m will be, where your log will be, whether it's log y or log x. All right? So log y, you've got, when I sorted out just now, I rearranged the formula out just now, or the equation out just now, I know that is another log, that's another log number, that's all.
Or you log the x
Right.
instead of
Now go on to the log-log graph. Here, in this case, the x is a log, the y-axis is a log as well. And you can see that I've got function of x to the power of 2, x to the power of 3, and fx. When you plot it in the log-log graph, everything is a straight line.
Yeah.
Just notice one thing, log graph does not have a 0, all right? Because there's no log whatever equals to 0. There's no log 0, sorry, my fault. There's log 1 equals to 0. Now, so example 3 this time, can you show algebraically all exponential relationship of the form y equals to ax to the power n will appear as linear relationship on the log-log scale? Now, because you're looking at log scale, what you really need to do in this situation is take log on both sides. You need to take log of y and log of left hand side and log of right hand side. So if you take log of y, let's say log 10, base 10. Log of ax to the power of n is just log y equals to log a plus log x to the power of n, right? Because it's log a x, log of a times xn, which is log a plus log of x to the power of n. And you know that there will be n log x. Now log y is based on x. Log a is constant.
Yeah.
N is therefore the gradient, right? Yeah. So c equals mx again. Yeah. So can you therefore describe the gradient of the line formed by the line y equals x cubed on log in base 10? So if I do that, what would happen? A is actually 1, correct?
Probably just like.
So log y equals 3 log x. So therefore, I just indicated to you that it's a gradient. So for every increase in 1 unit of log x, there's an increase of 3 units of y. All right? Just a gradient, that's it. 1, 1, and 3. So a generalization, a log plot, you have a log y plus m of log x plus c, where r is the base of the log scale.
So can you go back one slide?
All right, actually, the 2 lessons goes on very smoothly. That really links to the application of log scale. All right. So that is your log plot and log plot and log linear plot. So what we're going to do is going